Okay, this is the pre-class lecture video for Friday, October 5th. And we're starting chapter 5, which deals with a new type of stereoisomer. But before we do that, let's review some of the other types of stereoisomers that we have talked about and make sure that we're all clear on the definitions. So first, what are stereoisomers? They're compounds that have the same structural isomer. They are the same structural isomer, but they have different three-dimensional shapes. That's the generic sort of definition of stereoisomers. We've talked about several specific types of stereoisomers over the course of the last few weeks. The first were conformations, where you have compounds that have different three-dimensional structures, but the key is that they could be interconverted by rotation around the carbon-carbon single bond. So our anti-butane to eclipsed butane to gauche butane to the other form of eclipsed butane, those were all conformations, as were our chair and boat conformations of cyclohexane. We also talked about cis-trans isomers, and we talked about cis-trans isomers of cyclohexane. And for the cycloalkanes, that's a different type of stereoisomer where you cannot interconvert by rotation around the single bond. So for instance, our cis-dimethyl 1,2-dimethyl cyclohexane is different than trans, and they cannot be interconverted. And our double bonds also had that same cis and trans notation because, again, they could not be interconverted unless you have a carbon-carbon bond that is broken. So those are the two types of stereoisomers specifically that we've talked about so far. Now we're going to add a third type of stereoisomer, which is incredibly subtle. And that is what is called chiral molecules. So chiral comes from Greek, which means handed. And chiral molecules basically mean that we have mirror image stereoisomers, and they're not superimposable. So we're going to have a molecule, two molecules that are the same structural isomer. They have the same atoms bonded to each other, but they're going to be mirror images of each other, and those two mirror images cannot be superimposed. Okay, an example of chiral molecules, and I don't have a picture here, so I'll have to draw a crude version, are hands. Okay, these are sort of warped hands that I suppose look like birds. Anyway, so if you have your left and your right hand, they are mirror images of each other. So if you hold them up, you'll see that they're mirror images, but they're not superimposable. You cannot place your hands on top of each other, palm to back, or with both palms facing down, and have your hands overlap each other or be identical to each other. You could say the same thing for feet, and there are other examples of chiral molecules. So these two molecules that I've written here that have a carbon atom and then have four other atoms attached to them. Maybe this is a hydrogen, maybe this is like an OH group, maybe this is a chlorine, and I don't know, maybe this is a bromine. When a carbon has four different groups attached to it, it can exist in a left and right-handed form that are mirror images of each other. Now, just using the colored group here with the pink, the red, the blue, and the green, these two are mirror images, and you can see that from the way they're drawn here in the tetrahedral representation, but they cannot be superimposed. So if I try and overlap these two molecules, and if you can imagine me taking this molecule and sliding it over here and overlapping it there, what happens is that the two red and the pink groups overlap, but the blue and the green don't. If we go back here, see this green and this blue would not overlap, and the blue here, well, they would overlap. The blue and the green here would overlap. So in this case, two of the groups overlap, but the other two won't. And so these are non-superimposable molecules that happen to be mirror images. And so that's what we call chiral molecules. Later on, I'm going to call these two molecules in particular enantiomers because they're very specific. They are chiral molecules that cannot be superimposed. Okay? So this is a very subtle kind of stereochemistry. They're molecules that are mirror images but can't be superimposed on each other. And they can have huge consequences, as we'll see in a couple of minutes, well, or a few minutes, on how they react, particularly in biochemistry systems. Okay. Now, when I talk about a molecule being chiral, what I mean is that the molecule can exist in what we would call the left, we would call right now in quotes, the left and the right-handed forms. Okay, and I'll put more specific definitions to those in a few minutes. But that means the overall molecule is chiral. So there's two criteria that you have to meet for a molecule to be able to exist in left-right mirror images that cannot be superimposed. Number one, the molecule has to contain one sp3 hybridized carbon. And that one sp3 hybridized carbon has 4 different groups attached to it. So the molecule has to contain one sp3 hybridized carbon that has 4 different groups attached to it. And that's what we call the chiral carbon. So a molecule has to have at least one chiral carbon. Okay, and we'll talk about how we can differentiate and determine chiral carbons in a moment. Also, the molecule cannot contain what's called an internal mirror plane. And this will become more important in the next couple of lectures. We won't necessarily talk about the internal mirror plane for an overall molecule yet. We'll talk about what happens when an internal mirror plane slices through a carbon in a moment. So the first requirement is you have to have an sp3 hybridized carbon. That means that it has to have 4 groups attached, and that's the key. If it's only got 3 groups attached or 2 groups attached, not going to be chiral. So let's look at what happens if you have less than 4 different groups attached. Well, here's an example. How about a CH2 group? So let's say I take, and I may have my OH group here, and maybe I've got a chlorine here, but I've got 2 hydrogens attached to that carbon. Is that carbon chiral? No. Why not? Because it cannot exist in a non-superimposable mirror image form. So here's my mirror plane, here's my mirror image. Now, can I superimpose this molecule onto this one? Yes. If I took this molecule, and you can imagine this axis, if I rotated this molecule around this axis, so I put the green group, so I rotate this group here, and the pink group back here. What would happen is this would now be green, this would now be green, and this would be pink, and those 2 molecules would match up perfectly with each other. And I think maybe that's the final result that I did here. Okay, so here's my superimposable mirror image in essence. Okay, so if you have 2 groups that are the same, you can actually superimpose the mirror image on each other. Well, that means that molecule is not chiral, or that carbon is not chiral. It's only chiral if it's a non-superimposable mirror image. So as soon as 2 groups are identical, that carbon is not chiral. So that means that you can never have a CH2 group have a chiral carbon, and the carbon of a CH3 group cannot be a chiral carbon. The only groups that are left are CHs and quaternaries. And a quaternary carbon is one with 4 different groups attached to it, or 4 groups attached to it. Those are the only possibilities. Okay, so when we're going to start looking at molecules here in a minute, and we're going to try and pick the chiral carbons, we can go through and draw an X through all the CH3s, all the CH2s, because by definition they cannot be chiral because they are superimposable on their mirror image. You need to have 4 different groups attached to that carbon. Okay. Now this brings up the issue of the internal mirror plane. What do I mean when I say an internal mirror plane in the molecule? Well, here's what I mean. Let's say that I look at that CH2 molecule and I orient it sort of like this. I have 2 hydrogens pointing towards you. That's what the bold wedges mean. And then I've got maybe the oxygen, which is red, pointing away from you. And I've also got then this chlorine, let's say, pointing away from you. So I'm looking at the molecule like this. I can cut that molecule in half. And the left side and the right side are the same. And so this is what we call the internal mirror plane. And so anytime you can draw an internal mirror plane in the molecule and it cuts the molecule in half, any carbon that internal mirror plane goes through is therefore not chiral. Okay? So when you can draw an internal mirror plane in the molecule and make the left half and the right half, or the top and the bottom half match up, any carbons that cut through, or any carbons that internal mirror plane cuts through, are not chiral. Okay, and I'll use that test in a few minutes. So it's really kind of easy to determine that you have a carbon that's not chiral. The only criteria that's left is, well, what carbons are? They got to have 4 different groups attached to them. Okay. So let's look at some possibilities here. And let's go to this slide. So are there any chiral carbons in this molecule? The first one, which is 2-chlorobutane. Are there any carbons that have 4 different groups attached to them? Well, I'll write in my CH3, CH, CH2, and CH3. Are there any carbons in there that I can immediately eliminate as not being chiral or not having the possibility of being chiral? Sure. CH3s aren't going to be chiral. CH2s aren't going to be chiral because they have 2 groups, at least 2 groups the same. Now how about this one? Is this carbon chiral? Well, what's it have attached to it? It's got a chlorine and a hydrogen. Those are different. On this side, it's got a CH3 group, and what's it have over here? A CH2CH3 group. So this carbon has a methyl, an ethyl, a chlorine, and a hydrogen. It has 4 different groups attached to it. And so therefore, that carbon is a chiral carbon. And usually we put an asterisk next to chiral carbons. Okay, so we're not just going to look at what atoms or what groups are directly attached to the carbon. We're going to look at the whole group. So methyl is different than ethyl, different than chlorine, different than hydrogen. Chiral carbon. Okay. Can you go through limonene? Okay, this is limonene. That is a molecule that's found in orange peels. If you have any kind of citrusy drink or soda, it usually has limonene as a flavoring. Can you identify the chiral carbons in limonene? Well, here's what I'm going to do. I'm going to first of all write in my groups, And now let's go ahead and eliminate the ones that aren't chiral, that have no possibility of being chiral. CH3, not chiral. CH2, 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 CH3, CH2, definitely not chiral because they have two of the same atoms attached. We can eliminate the carbons in the double bonds from being chiral. Why? Because they're not sp3 hybridized. Now that leaves us one left. That leaves us that CH. Is that chiral? Well, let me go back here and let's put in that chiral. Let's put in that carbon again. I'm going to put it in blue. Does this carbon have 4 different groups attached to it? H, it's got this entire group attached to it. It's got this entire group attached to it. And it's got this entire group attached to it. Are those 4 different groups? Well, are we in agreement that H is different than this group? Now, are we in agreement that this group is different than this group? Well, this carbon, this group has a CH2 attached to a CH2. Down here I got a C double bond. That's not a CH2, so therefore this group over here is definitely going to be different than that group there. Now, where people may have some issues when we first start this process is, okay, here's a CH2 and here's a CH2. Well, those are the same groups. No, those are the same immediate groups. We got to continue on. What's attached to, it's not just this CH2, it's what's attached to it. What's attached to this CH2? A C double bond H. What's attached to this CH2? A CH2. Are those two groups the same? Nope, they're not the same. So therefore, this group is different than this group, is different than the hydrogen, is different than the C double bond group. So therefore, this is a chiral carbon. Okay. Let me show you an somewhat easier test. Remember that internal mirror plane of symmetry, when it cuts through a carbon, that carbon is not chiral. Is there any way that I can draw a plane through this carbon and cut the molecule in half? In other words, is there symmetry around this carbon? No. There's no way to draw a mirror plane in this direction or this direction or this direction. There is no mirror plane that cuts the molecule in half through this carbon. Therefore, it's chiral. Okay, and that's sometimes an easier test. Any mirror planes that cut through carbons, those carbons are not chiral. All right, how about this? How about the last one? 1,4-dimethyl cyclohexane. Are there any chiral carbons in this molecule? Well, I can eliminate the CH3s. I can eliminate the CH2s. And all I have left is this carbon hydrogen, are these two CH groups. Are those two carbons chiral? No. You might say, hey, there's a mirror plane this way. And I'd say, big deal. Because this mirror plane that cuts this molecule in half doesn't go through any carbons. So right now, that's not an important mirror plane. Later on, it will be. Now, what if I draw a mirror plane this way? If I draw the mirror plane that way, it cuts through this carbon and this carbon, so therefore, they aren't chiral. And so, there are no chiral carbons in this 1,4-dimethyl cyclohexane. Okay? So there has to be a carbon with 4 different groups attached to it. Basically, that eliminates everything but CHs and carbons that have 4 different things attached to them. If you can pass a mirror plane through a carbon, it ain't chiral. Okay? So that's our first step, is we've got to be able to identify chiral carbons in the molecule. And that's usually our best ways to do it, is to eliminate all the CH2s, all the CH3s, all the non-sp3 hybridized carbons. And then when we get it down to CHs and quaternary carbons, easiest thing to do is apply the mirror plane test. If you cannot pass a mirror plane through that carbon, then it is chiral. If you can, it's not. Okay. Here's 2 more. If you think you got it, stop the tape and identify the chiral carbons in these 2 molecules. Okay, hopefully you've got them. Let's start with the molecule on the right. In biology, this molecule is called an alpha amino acid. We're just an amino acid. Where's the chiral carbon in this molecule? Well, as long as this R group isn't an H or an NH2, that's the chiral carbon. Now, if it is an H or an NH2, then that carbon's not chiral. But for most of the amino acids, actually all but what, 1 that's got a CH2 here, those amino acids can exist in a left and a right-handed form. And surprisingly, only 1 form is formed in nature. But we'll come back to that. Here's the structure of a steroid. How many chiral carbons are in the steroid? Well, if you eliminate all the CH2s, you're left with this, 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 and this. Can I draw a mirror plane through any one of those CH groups, and they're all CHs? Can I draw a mirror plane through any of those CH groups that cuts the molecule in half? No. There's no mirror plane that cuts the steroid in half. And so therefore, this one has 6 chiral carbons. And over here, the amino acid has 1 chiral carbon. Okay? So it's relatively easy to eliminate the possibilities, and then when you're left with a CH and a quaternary carbon, then go ahead and apply the mirror plane test to those. No mirror plane, it's chiral. Okay? So that's the first issue when we start talking about chiral molecules. What carbons in the molecule are chiral, have 4 different groups attached to them? Because if there are 4 different groups attached, then it can exist in this left, right, non-superimposable mirror image form. Now, enantiomers, the definition of an enantiomer, if I haven't said so explicitly, which I don't think I have, enantiomers are non-superimposable mirror image isomers. That's what enantiomers are, and there's a pair of them, the left and the right-handed versions. Okay. Now, if you have a molecule that exists in these 2 enantiomeric forms, in the left and the right-hand version, are there any differences between those molecules? Yes and no. Let's deal with no first. It turns out that enantiomers have exactly the same physical properties, except one. If I took enantiomers, they would have 2 enantiomers, they'd have the same melting point, the same boiling point. If I put them on a thin layer chromatography plate like you just did in lab this week, they'd have the same refractive index. If I injected them into the GC, unless it's a specially modified GC that I'll talk about later, they would have the same GC retention time, or sorry, refractive index. Sorry, if you put them on the refractometer, they'd have the same refractive indices. If you put them on a TLC plate, they would have the same RF value. All those physical properties are exactly the same. Solubilities are the same, etc. They differ in only one physical property, and that is how they interact with plane polarized light. That's it. That's the only way that they are different. So the question is, what's plane polarized light? Well, we need to talk about physics for a minute. First of all, electromagnetic radiation is what we typically call light. And it's called electromagnetic radiation because it's made up of electric and magnetic waves. They are orthogonal or perpendicular to each other. So a beam of light has both a magnetic wave component and an electric wave component. I'll come back to that video in a moment. Normally, when you see light, it has all the different orientations of those electric and magnetic field vectors, what we would call them. So if you have a beam of light, if I'm looking at this being, let's say, the electric field vector, it's going to be in all 360-degree orientations. The beam is going to be made up of all those different orientations. But there are things called polarizing filters that when you pass light through the polarizing filter, it allows only one orientation of the light to pass through. And this is what's sometimes called the picket fence model. There's my crude designation of a picket fence. So the polarizing filter only allows one orientation of the light to come through, and therefore we make what's called plane polarized light. Okay. Where do we encounter plane polarized light? Well, if we have polarizing sunglasses, then the light that we see is plane polarized. How do you know if you have plane polarized sunglasses? On a sunny day, which you may not see again here until May in Cleveland, look up at the sky, and if you turn your head or turn the orientation of the glasses and the blue sky changes its color or its depth of blueness, then you have plane polarized filters in your glasses, because the light that comes out of the sky is plane polarized. If you've ever looked at water or waves using plane polarized sunglasses, you'll actually see that there are different intensities of the light as it flickers off the water. Same thing's true off of cement. Sort of reflected light is oftentimes plane polarized. Now let's go back to this YouTube video, because I did have one of my own, but we'll just borrow somebody's from YouTube. Okay. So in order to do that, I'm going to continue recording, and now let's go to where is the stupid YouTube video? There. Okay. I will narrate. Here they're looking at a page from a whatever book or magazine or computer, and what they've done is they've put two plane polarizing filters. Notice that in this case it's very bright. Now as they turn it, what's happening is this. What's happening is that you're seeing these two. Let me go back here. At the beginning, this light that's over here is just normal light. The light coming through the plane polarizing filter is now polarized. And what you see is that's a little darker because not all of the light is being transferred through the plane polarizing filter. But now, if they put a second filter in front of it, stop, and what happens is that now the light that's passing through both of these filters actually has to be oriented so that both of these filters in this case are actually oriented in the same direction. So if both these filters right now are allowing light, let's say, going up and down in its electric field vector, it is allowing light of the same orientation to pass through both filters. But as I turn one filter to the right or to the left, what's going to happen is that it's going to begin to block the light coming through the first polarizing filter. If you could imagine a situation like this, where I have one filter allowing light of this orientation to pass through, and I have another filter that allows that same orientation to come through, then I'm going to see the maximum intensity of light go through the two filters. If I now begin to rotate one of these filters, what's going to happen is that the amount of light that has that same orientation is going to decrease. And so what's going to happen is they're going to orient the second filter so that it's completely perpendicular to the first filter. Well, at that point, if they're perpendicular to each other, what's going to happen is that no light is going to pass through the second filter, because light of this orientation can pass through the first filter, and only light that's perpendicular to that, which there isn't any, can pass through the second filter. You're going to completely block out the light. Okay, so let's go back to that video and see that happen. So notice, as they start turning the light, you can see they are starting to block out the light. So right here, these two filters are oriented perpendicular to one another. The light that's not passing through the first filter is coming through perfectly. The light that is coming through both filters, since the first filter is oriented, let's say, up and down, and the second filter is oriented so that light perpendicular to that passes through, there is no light perpendicular to the second filter passing through, therefore no light is coming through both filters. Okay, and so that's what plane polarized light is. It's light that is passing through a plane polarized filter, and therefore the orientations of the electric and magnetic field vectors are all one way. It's all one orientation. Okay. Okay. So that's what we use to interrogate enantiomeric molecules. And the person that came up with this was Louis Pasteur. He actually was the person that noticed this phenomenon. He wasn't the person that developed the polarizing filters, but he took basically crystals that came off of a cork in a wine bottle, which is called tartaric acid, and he basically took some of those crystals and looked at them under the microscope, and he noticed that the crystals were mirror images of each other. And then, as the story goes, he painstakingly separated them with tweezers into the left versions and the right versions. He mixed them in solutions and noticed that they rotated plane polarized light. So we have Louis Pasteur, the guy that invented milk, for that. And I know he didn't invent milk, but I told that joke when I first started teaching in Kansas, and I had a group of students waiting for me outside the door to tell me that he didn't invent milk. And I said, I know, it's a joke. So here's what happens. Take our plane polarized light, and when we pass that through a solution that contains chiral molecules, or molecules of only one orientation, the left or the right, those molecules rotate the plane polarized light. So they may start out at this orientation, and they're going to end up rotated by some number of degrees, which is called alpha. Okay. So this is how we know that we have a chiral molecule, meaning a molecule that is in one form or the other, a left-handed and a right-handed form. That's how we know that we have that molecule, because we have the molecule being rotated by plane polarized light. This is the only physical property of enantiomers that's different. And you might say, well, how is it different? Well, here's how it's different. When Pasteur did that experiment by painstakingly separating his crystals into the left and the right hand versions, or the mirror images, what he found was that one enantiomer rotated the plane polarized light to the right, and the other enantiomer rotated plane polarized light to the left. And it turned out that if their concentrations were identical, the number of degrees that they rotated plane polarized light was identical, except they were in opposite directions. So what they called this was, if the molecules rotate plane polarized light to the right, that's called dextrorotary, or what we sometimes call the D enantiomer with a big D. If it rotates it counterclockwise to the left, that's called the levorotary enantiomer. So overall molecules, when you determine their optical rotation, that's what we call this, is optical rotation, or the textbook calls this optical activity. One enantiomer will be the D enantiomer, and the other enantiomer will be the L enantiomer. So we have the dextrorotary and the levorotary enantiomers. And this is the only way that we can tell which molecule we have. It turns out that most of the sugars that we have are D sugars. If you put them in a polarimetry cell, you would find that they rotate plane polarized light to the right. Amino acids rotate plane polarized light to the left. And so the naturally occurring amino acids are L amino acids. And so polarimetry, which we'll do later on in the lab, we're going to take an Aleve tablet, which is a drug that is sold in one chiral form. We're going to determine whether it's the D or the L form that's sold. And I may do a demonstration on Friday with some other chiral drugs that are easily available. So enantiomers can either be D or L. Okay. And if you have molecules in the same concentrations, they have the same number of degrees, just opposite directions. So they rotate plane polarized light in opposite directions. That is the only physical property difference between enantiomers. Okay. Now, one of the things that can happen is that if you had a 50-50 mixture of enantiomers, then you would actually have no rotation. So if I take my sample cell and I mix 50% D and 50% L, what's going to happen? They're going to cancel each other out, so effectively I'm going to get 0 degrees of rotation. Well, it turns out that a 50-50 mixture of enantiomers is called a racemic mixture. Okay, and this, I'm going to assume, comes from the fact that there's another type of crystal that's formed in the winemaking process that you can find sometimes on the corks of wine, which is how Pasteur found the enantiomers. There's another type of crystal that was formed that was symmetrical that was called racemic acid, and it had no rotation. Pasteur actually mixed equal crystal mixtures of the D and the L forms and showed that they had no rotation. And so if there was this other acid called racemic acid, then that's where the racemic mixture, I believe, came from. So 50-50 mixture of enantiomers is called a racemic mixture. It will not rotate plane polarized light. Now, if you have an unequal mixture of enantiomers, of course, it will rotate plane polarized light. And we'll talk a little bit about that on either Monday or Wednesday of next week. Okay, so enantiomers, non-superimposable mirror images, the left and the right-handed form. Enantiomers come from the fact that a molecule has a chiral carbon in it, a carbon with 4 different groups attached. Enantiomers will rotate plane polarized light either to the right or the left, the D or the L enantiomer. Mix the two together in a perfect 50-50 ratio, you get a racemic mixture which has no rotation. Okay? So those are the physical property differences of enantiomers. What are the chemical property differences of enantiomers? Well, the chemical property differences of enantiomers are pretty important. It turns out that enantiomers, okay, whether you have the D or the L form, the left or the right-handed form, when they are reacting with other non-chiral molecules, then they react the same. Okay, so they react the same with other non-chiral molecules. Here's my analogy for this. We know that our left and our right hands are chiral. Do we have left and right-handed gloves in the lab? No, there's no box of left-handed gloves and right-handed gloves, because if you looked at the glove, okay, here comes another poor drawing of a hand. Billy says the right number of fingers. The gloves in the lab have a mirror plane that cuts right through the center of the glove. Not this way, but horizontally here in the plane of the screen. So it turns out that that glove is non-chiral. So no left or right-handed, nitrile gloves in the lab. But when the thumb is out, like a winter glove, like a ski glove, that glove becomes chiral. And your chiral hand reacts differently with the chiral gloves. Try and put a left hand into a right-handed glove. It doesn't fit the same as a left hand in a left-handed glove because the gloves are chiral. So enantiomers react the same with other non-chiral molecules, but they can react differently with other chiral molecules. Okay, and when I say they react differently, sometimes that difference isn't very big, sometimes it's huge. Okay, so they react differently with other chiral molecules, but they react the same with other non-chiral molecules. Okay, so this is why we have shoes for the left foot and the right foot. And if we have sort of a, if we have some sort of shoe that fits on either foot, then it would be non-chiral. I don't know that example as good as I know the gloves. Okay. Where is this important? That you have chemical properties that are different between the enantiomers. Biological systems are for the most part made up of one enantiomer. L-amino acids make proteins. The chiral building blocks of the L-amino acids that make the proteins chiral. Enzymes are typically chiral. So when chiral molecules go into a biological system, they will encounter other chiral molecules, usually of one orientation, D or L. And so therefore those molecules will react differently if they are in their different enantiomeric forms. Back when we talked about functional groups, I showed you this example of thalidomide. Thalidomide was used as a sedative in the 1960s. It existed at that time. The drug that was administered was a 50-50 mixture of the D and the L forms. It was a racemic mixture. But the two chiral forms of that drug had two totally different reactions. One enantiomer was a sedative. The other enantiomer caused birth defects. And so the children that were born of women who took thalidomide had severe birth defects. Okay? I would not encourage you to Google search that, but if you're interested in that, you will see those online. Again, that's not something I would suggest doing for the faint of heart. But thalidomide was then immediately taken off the market because it was being sold as a racemic mixture. Now, in theory, can you separate the two enantiomers and just sell the drug that was a sedative? Apparently that's being done, only they changed the name from thalidomide to phthalimide. The problem is that if the phthalimide gets in your system and somehow undergoes some sort of reaction that changes the D into the L form, or vice versa, it's as good as taking the racemic mixture. And the other thing is you have to get rid of all of the molecule that created birth defects. If you go back and look at that lecture, if you look at the poster that's outside of the organic lab, phthalimide sold so many millions of dollars of that were sold back in 2007. A risky proposition, to be honest with you. I'm not quite sure how that drug company does it, but it does. Here's another example, glucose. If you mix glucose with yeast and water, you get fermentation. And you see bubbling, CO2, if you've done that in biology. That's how you tell fermentations occur, because you get CO2. D-glucose is the naturally occurring form of glucose. Put that in with your yeast, and you get lots of CO2 gas, lots of fermentation. Put in the unnatural L form, you get no fermentation. So these two sugars react completely differently with the enzymes in yeast. One gives fermentation, one gives nothing. If all the glucose in the world changed from D to L, we would be pretty hungry and probably dead, because we couldn't metabolize the L-glucose. Okay? Sometimes people talk about giving students the Alice in Wonderland thing, where if you walk through the mirror, all of a sudden you would become a mirror image, and what biological processes would exist in their mirror image form in the mirror image Alice, or would she die because all of the biological reactions don't work anymore? I'm not going to give you that, but that's something that people ponder. Last example, L-DOPA, D-DOPA. This is a treatment for Parkinson's. L-DOPA, that enantiomer, is effective. D-DOPA doesn't work at all. So again, when the L-DOPA reacts with a chiral molecule in our biological system, you can get the chemical reactions that help alleviate Parkinson's. D-DOPA, the other enantiomer, doesn't react, which is a different kind of reaction. So physical property differences then, the only physical property differences for enantiomers are plain polarized light. The chemical differences are with a non-chiral molecule, enantiomers react the same. With a single chiral molecule, they can react quite differently, or not react at all in some cases. Okay, so those are the differences between enantiomers. Okay, configurations of chiral carbons. Now, I've been talking about these chiral carbons and these molecules being in their left and right-handed forms. When we talk about molecules, the overall molecule, we're talking about whether the molecule is D or L, whether it rotates plain polarized light to the left or the right. Now later, we're going to talk about molecules that are in their left and right-handed forms, or their D and L forms, that have more than one chiral carbon. We're going to start easy with just one chiral carbon. But when we talk about molecular chirality, we're talking about D and L. Every single chiral carbon has what's called a configuration. Okay, so configuration, the configuration is the exact three-dimensional structure around a chiral carbon. Okay, and those are designated by being either R or S. So every chiral carbon in a molecule, and we're going to start with molecules that have a single chiral carbon, but every chiral carbon in the molecule is either designated as R or S. Okay. Now, how we get R and S, I'm going to leave for Monday's lecture. But I just want to introduce this idea. So if I've got a chiral carbon, I'm going to have to be able to tell you whether it's R or S in its configuration. And there's going to be a series of steps in order to determine R or S. Even molecules that have a single chiral carbon, in that case the chiral carbon is either R or S, but the molecule is either D or L. Well, it turns out that there's no overall relationship between R and S and D and L. Some D molecules have the L configuration, or some D molecules have the S configuration. Some L molecules have the S configuration, and vice versa. So when I draw the structure of a molecule and I determine if this is R or S, I cannot tell whether it's D or L. Okay? There's no relationship between R and S and D and L. People have tried to put databases and see if there's correlations, and there's probably a correlation here or there, but there's no direct relationship between D and L and R and S. The only way to make that connection is experimental. What we do is we basically isolate the molecule. And when we isolate the molecule, we determine whether the configuration around the carbon is R or S. I may get into that later on. That is not a trivial fact. And considering the fact that when you have to sell a drug like Aleve, which is right now a generic pain medication, I mean, you have to determine for the FDA whether you have the R or the S configuration on that chiral carbon. And you have to use a technique called X-ray crystallography, and it is not an easy thing to do. But if you can get the molecule and if you can determine if the configuration is R or S, then it's easy. You then take that molecule, you pop it in a polarimeter, and you determine whether it rotates to the right or to the left. So you have to make those experimental relationships. You cannot make them on paper. And two different molecules can have two different correlations. So the R of one molecule may be D, but the R of another molecule might very well be S. Okay, so there's no relationship between those. And when we do our lab experiment with the Aleve tablets, that's going to become perfectly clear, because we're going to change one molecule and we're going to change the molecule's identity, but not change its configuration. And the molecule is going to be D in one case and L in the other. And I did nothing to the chiral center. All I did was change the molecule itself. Okay? So, R and S are the configurations around that chiral carbon. So now we need to learn the rules for determining whether a molecule is R or S. And I'm thinking that it's time I shut up and stop the tape. And so what I will have for your pre-class lecture on Friday will be, how do we determine R and S for a chiral carbon? And so what we will do some problems then for on Monday's class on determining R and S. What we will do on Friday is we will go through and identify chiral carbons as well as answer questions. We'll do, here's a molecule, how many chiral carbons does it have, and which ones are the chiral carbons on Friday. And then if everybody gets that, maybe I'll move a little bit ahead and talk about how to determine RNS. But that's my plan for Friday. Okay. So this actually takes us through only half of section 5.3 of the textbook, because section 5.3 does all the RNS. I'm going to do all of that for Monday's pre-lab lecture. Okay.